When you look up into the sky on a nice clear night, looking at about 2,000 stars in our galactic neighbourhood, you're not really seeing the full picture. While you do see thousands of stars on a good clear night, there are actually planets orbiting those stars, which are invisible to us. On this graph contains how we found exoplanets since 1988. The red parts of the graph mean we found a planet by direct imaging. With direct imaging, actually looking at the planets through a telescope, taking such a small percentage of this graph, how are we actually finding these exoplanets? First off, why does direct imaging not work very well? The reason is because unlike stars, planets aren't actually creating any light. If you were a fair distance away from both the Sun and Earth, the Earth would be millions of times less bright than the Sun, which means actually seeing Earth would be extremely hard. Stars from a distance cause glare, which means you can't actually see the planets orbiting around it very easily. So if we can't actually observe most of these planets, how are we finding the planet? The main way to find exoplanets is to look at the effects which these planets are causing on other things. The most popular way we have found planets over time is called transit photometry, which is the easiest method to wrap your head around. Using the transit method, we can get the size of these exoplanets and also their orbital period. The transit method involves pointing a space telescope at a region of space and watching the stars. When a planet crosses over one of the hundreds of thousands of stars we're looking at, it will cause a slight drop in the amount of brightness that we're receiving from the star. Planets such as Jupiter, Saturn and other quite large planets cause a 1% brightness drop, compared to the planet the size of Earth causing a mere brightness drop of 0.01%. You can confirm whether or not it was a planet which you observed by seeing if there's a similarity on how often that star is experiencing a brightness drop. If this is happening at regular intervals and the brightness decrease lasts the same amount of time, you can begin to confirm that there is quite likely a planet orbiting that star. With a Kepler telescope measuring the brightness of about 160,000 stars every couple of minutes, we are able to detect these small blips in the amount of light we are receiving from these stars. Just because you found a new exoplanet using this method doesn't mean you should be out partying just yet. In single planetary systems, there might be a 40% chance that you've received a false positive, which means we have to use other methods to confirm if this is a planet or not. Radial velocity is another method we can use and is also a way we can confirm whether or not a planet we found using the transit method is actually there. The radial velocity method is looking at the very slight change of velocity a star exhibits when both the exoplanet and the host star are orbiting around their common centre of mass. This is because all the planets in the Sun are orbiting not the Sun, but the centre of mass of the whole solar system. For example, you can see in this that the objects are orbiting around the centre of mass, which is a little line down the middle of your screen. Radial velocity takes a lot of time. Jupiter, for example, causes the velocity of the Sun to change by about 12.4 meters per second over the period of 4 years, and tiny planet Earth causes the Sun's velocity to change by about 0.1 meters per second over a whole year. This means we have to take very long observations of these stars to pick up this change in velocity, which potentially means you're searching for years. Pluto wouldn't be very observable if someone's to be looking at our solar system wondering if there are any planets in it. With it being so small and so far away from the Sun, it only causes a 0.000003 meters per second change in the velocity of the Sun. But how are we actually seeing these changes in speed if they're actually quite tiny? We can detect the shift in the wavelength of the light which the star is emitting, with the light being blue shifted when it's moving towards us and red shifted as it moves further away from us. The magic all happens when we bring relativity into finding planets, with gravitational microlensing being the third way we can detect exoplanets. Gravitational microlensing really relies on one star passing in front of another, so we have a star far off into the distance and then a closer star coming in from the side. When the star is in line with the distant star and us on Earth observing this, the light from the distant star will be bent and also magnified. On a brightness against time graph, we would see something like this as the closest star passes in front of the distant star, causing an increase in brightness, because the closest star's gravitational field creates a gravitational lens, which then magnifies the light of the furthest star. But what if there's actually a planet orbiting the star? If there is, the planet will cause a small blip on the graph, due to the planet also acting as a gravitational lens for a really short period of time, which might only last a few hours. The problem though with gravitational lens is that you only really have one shot. That sort of alignment is really unlikely to happen again compared to the radial velocity and transit method, which is happening all the time as you're not relying on a distant star or the off chance of stars aligning and you being able to catch it in time. With only about 1,000 of these events ever happening in the last 10 years, we have a lot more success with the transit method, which is our main way of finding exoplanets. With these methods working together, we've managed to confirm the existence of 974 planets, and there have been about 3,846 candidate planets just found by the Kepler Space Telescope. We're really beginning to learn more about our galactic neighbourhood. We've only discovered a tiny fraction of the 480 billion exoplanets thought to exist in our galaxy alone. It's amazing to think that there could quite possibly be about 64 septillion planets out there in the whole universe, just waiting to be discovered.